Okay, so this is our second video doing the same problem on the y double prime minus y prime is equals to ln of t. We have to solve this differential equation. And the conditions are y of 0 is 0 and y prime of 0 is 0. The solution is there, and we already found this solution in the previous video where we solved by the Laplace transform, right? Where we solved using Laplace transform. And in that video, I promised that we will also make a new video where we will solve this using variation of parameters, using the fact that our solution is in the form of complementary function plus particular function. And to find the particular function, we will use variation of parameters. So if you want the solution using Laplace transform, you can just take a link over here in the top right corner. There should be a link. Okay. Now for the variation of parameters, let's start. So we have this differential equation y double prime minus y prime is equals to ln of t. So first of all, we need a complementary solution, right? We know that solution is in the form of the complementary function plus particular function. And basically, the complementary function is the solution to the differential equation, the homogeneous differential equation where the right side is 0, right? So it's not too hard to solve this one. We know that for such differential equation, we just use the characteristic equation of this differential equation, right? The spelling of characteristic is wrong, I'm sorry. Okay, so the characteristic equation of this differential equation is basically r square minus r is equals to 0. So r times r minus 1 is equals to 0. R is equals to 0 or 1, right? So therefore, the complementary solution, just the solution becomes, we know that it will just be c1 e to the power the first r1t plus c2 e to the power r2t, right? Where r1 and r2 are the solutions. So this is c1 e to the power 0t plus c2 e to the power 1t. So therefore, our complementary solution is just c1 plus c2 e to the power t, right? And now, we know that our particular solutions, particular solutions can be in the form of some function u1 of t times our. Okay, so over here, I will write y1t plus u2 of t times y2t, where u1 and u2 are the functions to be found out. And this y1 and y2 are basically these two solutions, e to the power r1t and e to the power r2t. In this case, e to the power 0t and e to the power 1t. So that means e to the power t. Sorry, this is not e to the power t. So in this case, this will just be 1 and e to the power t, right? Okay, now, so yeah, I guess you guys don't forget that this is y1, this is y2. And if we are able to find u1, u2, we will have the particular solution, right? And I guess you guys know how to find u1, u2, right? There are formulas which you can derive, but for now, we will just use it. U1 will just be negative of the integral of y2 of t times. Now this over here, the ln t, I will denote this by g of t, okay? So yeah, you y2 of t, g of t by Wronskian of y1, y2 dt. This is how we find u1. And I will tell you how to find Wronskian. And u2 is just integral of y1 of t, g of t divided by Wronskian of y1, y2 dt. You can derive these formulas. Well, what you would do is you basically just try to put this particular solution into our main differential equation and then try to solve for u1, u2. You can also make some constraints for u1, u2, and that's how you get the solution. So definitely you can definitely check the derivation. It's not too hard, but for now we will just go with the solution. Now, how to find Wronskian? The Wronskian is basically of y1, y2 is defined as y1, y1 prime, y2, y2 prime, right? And now y1 is just 1, y2 is e to the power t. The derivative of 1 is 0, the derivative e to the power t is e to the power t. And e to the power t minus 0 is e to the power t. Notice that Wronskian should never be 0, because if it's 0, we cannot really divide by 0, right? And yeah, it's never 0, and that's a good thing for us. So, u1 is negative of y2 of t is just e to the power t, z of t was ln of t, by Wronskian is also e to the power t dt. So u1 is negative of the ln of t dt. So this is negative of t ln t minus t plus c, right? This integral of ln t is a standard integral. You can just use integration by parts. So yeah, we actually don't need plus c, because even though you put a plus c over here, that will just give like c 1 y1 t plus c2 y2 of t, which we also have in the homogeneous solution, the complementary solution, right? So that's just a redundant thing. I can actually erase this plus c. We don't need it. So and this becomes t minus t ln of t. So this is how you want. The u1 is easy. u2 can get slightly complicated. u2 is now integral of y1 of t is just 1, and g of t is ln of t, and the Wronskian is e to the power t dt, right? Now this is e to the power t ln of t dt, right? And now to solve this integral, we can use integration by parts. So this becomes ln of t, and integral of e to the power t is e to the power t. I'm taking this as u and this as b, okay? Minus integral of derivative 1 by t is 1 by t. Derivative of ln of t is 1 by t, and then the integral of e to the power t is e to the power t itself, so dt. So this is e to the power t ln of t minus e to the power t by t dt. Okay, over here, the good thing is, there's really no negative sign over here, and that's actually a problem, because when this goes in numerator, there should be a negative sign, right? So this becomes negative t by negative 1, and this becomes negative t by negative 1. I'm sorry for that. And this becomes a negative, and this becomes a positive, and there's a negative sign. Okay, now that's good. That's good, right? Okay, and now we know that the derivative, and now I guess you guys know about this function, the derivative. There's this ai of t function whose derivative is just e to the power t by t integral dt. And now if you substitute t as negative t, if you substitute t as negative t, this is called exponential integral function. This just becomes e to the power minus t by minus t times minus dt, so that's again t dt. So this is actually just plus ei of minus t, and therefore the solution is exponential integral function of minus t minus e to the power t ln of t. Sorry, this is not e to the power t, this is e to the power minus t. I'm sorry, guys. I'm making a lot of mistakes. Okay. I guess it's good now. Also, we have the answer, like to take at the end, so there's really no problem. So yeah, now we have u1 and u2, so we are good to go to find the uh this is this is already our complementary function. Now we can find the particular function. We know that particular function is just u1 y1 t plus u2 y2t, right? So our particular function, our u1 is just t minus t ln t, and our y1 was just 1 plus our u2 is just ei of minus t minus e to the power minus t ln t, and y2 is just e to the power t, right? So this is the particular function, t minus t ln t plus e to the power t ei of minus t minus ln of t, right? So the solution is basically just complementary function plus particular function and complementary function is c1 plus c2 e to the power t, plus particular function is just t minus t ln t minus ln t plus e to the power t ei of minus t. Now to find the c1 and c2, we will use the initial condition. So like this is the problem of not using Laplace transform, because if we use Laplace transform, we don't really need to like again use those initial condition because that's used at the beginning. But over here, that's the trouble. And we'll basically use the fact that okay, I'll do it later on. So yeah, we have y of 0 is equals to 0, y prime of 0 is equals to 0, right? So yeah, this is 0 plus c1 plus c2 plus 0. Now t ln t, this is 0 times infinity. But if we take limit, this will just become 0. And yeah, there's this thing. Now limit t goes to 0 of e to the power t ei of minus t minus ln of t. This actually just goes to euler-mascheroni constants, and it's on the viewer to prove it for themselves. Like this will just become euler-mascheroni constant, this limit over here. Like you can just go on Wikipedia, and with there you can actually see the Ramanujan approximation of the exponential integral function. And in the Wikipedia, like if you go with the Ramanujan approximation, and it's evident from there. Also, there are other proofs. You can do it for yourself. Ramanujan approximation. Okay. Now, yeah, we get this first equation. Now, again, if we just differentiate this, this will just become c2 e to the power t plus 1 minus 1 minus ln t minus 1 by t plus this becomes e to the power t ei of minus t plus e to the power t times. Now, its derivative will be okay. Uh, guys, I'm sorry. Okay, I'm sorry about one thing, that actually its derivative is just e to the power t by t, not with the integral. Actually, uh, their definition is with the integral, right? The definition is with the integral, but if we differentiate this, we won't get the integral. I'm sorry for that. I'm sorry for making that mistake. Okay, now I think I'm sorry, guys. I'm sorry for making that mistake. Okay, and now over here I realize, because now, yeah, if we use product rule, e to the power t times the second expression as it is, now e to the power t times the second expression is just e to the power minus t by t. So therefore, our y prime of t is c2 e to the power t, and this cancels out, and also minus 1 by t and 1 by t cancels out, so minus ln of t plus e to the power t ei of minus t. Again, if we put 0, y prime of 0 is 0, this is c2 plus the same thing, limit t goes to 0 of e to the power t ei of minus t minus ln t. I already told you that this is Euler-mascheroni constant, so c0 is equals to c2 plus Euler-mascheroni constant. That means c2 is negative Euler-mascheroni constant, and since 0 is equals to c1 plus c2 plus Euler-mascheroni constant, c1 will just be 0. So that means our solution will be, therefore, our solution will be 0 negative Euler-mascheroni constant e to the power t plus t minus t ln of t minus ln of t plus e to the power t ei of minus t. And that's a good solution. Also, if you want to check the solution, you can again find the double derivative from this expression over here, and you can check that the y double derivative minus y dash will just be ln of t. You can check it in that way, right? Or also we have the answer, we can check with the answer as well. So negative of rational constant e to the power t plus t minus t ln t minus ln t. Is it same? Is it plus t? Yeah, plus t. Yeah, okay, fine. And then e to the power t eif minus t to the power t eif minus. Yeah. So that's the correct solution, and we solved it using the variation parameter. I think this one is shorter than that is Laplace transform. Because in Laplace transform, I actually went into detail, but over here I skipped a lot of details, right? So that's what makes it easier. And yeah, this is solution. And also, if you want the solution in Laplace transform, it's also in the description. And yeah, so that's it, guys. Hope you enjoyed the solution. So it definitely reviews your concepts of the variation of parameters, the Wronskian, and also the exponential integral function and some limits. So yeah, that was it. Hope you enjoyed the video. Thanks for watching, and I look forward to seeing you in the upcoming videos too.